Let's continue. So yesterday we looked at the graph of some limesons and rose curves, and today we want to look at a couple other graphs. You had an opportunity to look at spirals last night too, a little bit. There was one of these at least. I don't have too much to say about it except that like you get a spiral. So, it's a little hard to graph it on this particular coordinate grid, so we'll deal. It's okay. So let's just do what we normally do, kind of empirically plug in some points and just see what we get. If you plug in 0 for theta, it's pretty clear that you get 0. So I'm all about that. There it is. If you plug 0 in, you get 0. What if you plug in like 2 pi? That is, we come all the way around. We get like approximately what? Yeah, we get like, well, it's about 6.28 over 10, so it's like about 6.6, right? So by the time we come all the way home, we're like right about there, say. It's like 6/10 of the way out. You know, the R value is like approximately 6.28. So what does that mean? That means I did this, right? It kept getting bigger and bigger. And then as we go around, it's going to be another, like every time, it's going to, like what if I go around 4 pi? It'll be approximately, huh? Oh, there wouldn't be an exponential there, right? It would just be another 2 pi away, right? Right, and the distance between these levels, I didn't draw that very well right there, but the distance between each level should be approximately the same. Each distance between the spirals. So feel free to graph this on your calculator. It would look best though if you do it with you know, a theta going from 0 to whatever, something bigger than 2 pi, whatever you want, 4 pi, 6 pi. It's pretty, yeah.
It is spooky with a black background.
It is spooky with a black background. Yeah. Anyway, so have fun with the spiral. I don't have much to say about it. What happens if you let theta range from a negative value to a positive value, like from negative 2 pi to 2 pi? Then it gets crazy. Because why? You actually do get a spiral going the other way too. So yeah, then it doesn't look as spirally though. So maybe we restrict it to just positive values for the sake of calling it a spiral. If you include negative values, then you kind of get 2 spirals, right? Do you do that with your hand? Yeah. You'll see on your calculator what I mean if you graph it. Okay.
Does it do it with its fingers?
Huh?
Does it do it the same way with its fingers?
Yeah. All right, let's take a look at a historical graph that's useful, that's interesting in like a historical sense, but not maybe in a use that. I don't know that it comes up that much, but it's called a lemniscate. That's how I'll say it.
It's like Lemniscate.
So the first thing I noticed about this is that this equation that we're about to graph looks pretty similar to which graph does it look similar to? The one that we were just doing. If this was an R instead of an R squared, it would just be a rose curve with 4 petals, right? So that's my intuition here too. I feel like this is going to be basically like a rose curve with 4 petals, kind of. But what does this R squared do to my life? I might think, well, R equals, you could maybe write it that way, I guess. Maybe or maybe not. Maybe do I need that plus or minus? That's a good question. I don't know. Let me think about it. All right, so then, like we always do, let's plug in some points and just kind of get a feel for this. All theta. So if we get I don't know, what happens when you plug theta equals 0 in? What do you get? You get 4? Okay, so in the 0 direction, we'll go out 4 units. 1, 2, 3, 4. Yay. If we plug in pi over 4, what do we get? You get 0. So this does come in and touch the pole. That's good. If you plug in pi, what do you get? If you plug in pi, you get 4. 1, 2, 3, 4. And actually, if we plugged in 0, technically when we plugged in 0, we got plus or minus 4, didn't we? Because both satisfy the equation. Theta equals 0, comma 4, and theta equals 0, comma negative 4, both satisfy. Excuse me.
Technically just
Other way
take
around.
the 4 out, or does it? Like you could leave this.
You could pull it out. It's nice here. Great. I love what we're doing. And then since I said this is like a rose curve with 4 petals, I kind of expect maybe if it's similar to a rose curve with 4 petals that we'll get another one in the pi over 2 or 3 pi over 2 direction. So what happens when you plug theta equals pi over 2 in? What do you get?
Not available.
Doesn't work.
Not available. I like that. Not available. It doesn't work. Yeah. True. Do you all see the issue? If you plug pi over 2 in, what happens?
Get eyes.
You get something imaginary, right? Because you get something, you get a square root of a negative, or up here we're asking to square something and get something negative, however you want to say it. So in the pi over 2 direction and the 3 pi over 2 direction is similar, you get nothing. It's unavailable. I like that. And in fact, we could go further. It's not just at that point. Thanks, Justin. It's not just at that point. It's any time at all that we have a negative value out of cosine of 2 theta. So when is cosine of 2 theta negative? Well, it's not just at those 2 points. It's actually like anywhere in between pi over 4 and 3 pi over 4, it'll be a negative value. And anywhere between 5 pi over 4 and 7 pi over 4, it'll happen to be a negative value. So in the end, we actually only get 2 petals. There's one. And there's the other. Okay. Close. The correct movement is actually this. You can watch this on your calculator. It looks like this. And then wait, I want to make sure I do it. It'll come around. It'll do that one, and then it'll do this one here. Yeah, I was right. So it's going to go this. And then it's going to wait, and then it's going to do this. Watch your calculator do it. It'll do it the way I just did it. Yeah, it's like it's trying to compute unavailable values for a few moments. That's when it's like drawing the imaginary petals. You can imagine they're like kind of 2 that it's trying to draw, it's thinking about, and then it returns to graphing real values. Okay, you'll see what I mean. Feel free to graph it. So that is the Lemniscate. It's also the figure, you guys, by the way, that that we've kind of captured in mathematics iconically in an artistic way that we use to kind of use. This is the typical symbol for infinity. Yeah, is a Lemniscate. So embody this look of limitlessness, smooth, nice curved thing. I don't know, but it's more of a feature of history than anything. If someone wanted to graph the same thing, replace the cosine with a sine, how would that go? How would that look if this was a sine instead? Well, I guess I should ask. Yeah, that's a good question. Yeah, would it be up and down?
No, it would be like crooked.
Yeah, remember the 4-petal rose curve? The 4-petal rose curve with a sine in there, it kind of looks like that, right? With the pi over 4, 3 pi over 4, etc. So yeah, it would actually be up along pi over 4, and down on 5 pi over 4 as well. First and third quadrant, yeah, is where it would live. I can't see it anymore, but I think, yeah, that's right. Yeah. Oh yeah, on your calculator it won't graph real close to the origin because your calculator is just a machine. It can only calculate, it can't actually do mathematics. But you and I know that it's as easy as just plugging pi over 4 in, then you'll see. So we're right. If you plug pi over 4 in, you get 0, so like your calculator's just being dumb. Okay. Finally, after all those cool curves, we're finally ready. You can handle it now for a lot. Okay. This will be in the homework tonight, yeah, too. Maybe you did the wrong homework. All right, so first question is, do you remember normal form of a line? No, you don't. Go ahead.
It's the
What is it?
P,
It has a P in it.
and the little our little guy with the lines around.
It does have a P and a phi, or a P. Yeah?
Oh, cosine of theta plus y sine of theta minus p
Equals what?
equals 0.
Ooh.
Good job. That's what it was thinking. Here, have some candy for thinking about it. Good job. I was thinking about throwing you candy.
was so happy there for a second.
Now I'm feeling bad.
Don't do it again.
It's what Steven said. We use phi instead of theta, but whatever, it's all good. So remember in this equation that x and y are variables, and phi and p are constants, right? Or p, whatever you like to say. I'm going to do what we've been doing. I'm going to convert this from rectangular to polar form by replacing each x and y by r cosine and r sine theta. Keep in mind again that what are the variables and the constants in this equation? R and theta are variables, aren't they? Phi or phi and p are constants. Okay? And then I'm gonna, just because I can't resist it, I'll factor out an r. Yeah, I'll get it, it's all good. Keep talking, okay? Okay. And what's going on here then? I moved the p over, I factored an r out just because I couldn't help myself. And then in the parentheses, what do you see?
Cosine difference formula.
Cosine difference formula. Good job, Maddie.
What? Oh, cool.
Yeah, it's the cosine difference formula. Did you think about that, Cindy? Did you see it too? Cindy thought about it too? Good job. Okay. All right. You get a Jolly Rancher too. Oh, no, Eric can eat it then. Good. It's the cosine difference formula staring you in the face. So there it is. We'll call that the polar form of a line. Again, where p and phi are constants, and r and theta are the variables at work here. Can you just refresh my memory on what those actually mean? I mean, down here it says it, but what does it physically mean? Like if I tell you that the length of the normal, p, is 10, and phi is the angle the normal makes with the positive x-axis is 2 degrees or something. What does that mean? Like how do you actually take that and draw the line? That's like, those define a unique line, Mr. Chase? Yeah.
Means you go from the positive x-axis up 2 degrees, then out 10 units, and perpendicular to the line that creates is the line you're defining.
Yeah, so we go like out at 2 degrees if that's the angle I gave you in its normal orientation. 10 units, and then you draw a line perpendicular to that spot. And that is, in fact, instructions that produce for us a unique line. There's not like another line that we can be talking about that meets the 2 criteria I said, right? So, anyway, so that's the way that goes in case you wanted to remind yourself. So, everyone graph this line, or do you need that still? Did you get your Jolly Ranchers? Okay, good. Graph the line, go.
On our calculator or?
No. By
Back
hand.
to the last one.
Maddie needs to go back to the last slide. Sorry, everybody. Is that good?
I'll think about it.
You sure?
I was thinking about it.
How about now?
Still thinking.
How about now? While I'm waiting, anyone know the capital of Cambodia?
Oh,
It's only out of where your hands.
That's right. Yeah,
Where?
All right, do you have it, Maddie? Is that buy you some time? Okay. Grab this, finally. Here we go. Phew.
I used to put having a stand up.
It's not clear.
There's some way of making this. You can juggle such balls. Can you juggle all the candy in that bin at once?
Yeah.
Are you guys going to talk to juggle and they catch the ball? Why would you say that?
Whenever you're ready.
Shut up, you're a bot.
You don't have to convert it to anything. Yeah, do you have to like convert this to rectangular coordinates to do this?
Yes,
No.
absolutely.
You don't.
That's
You
the only
could.
way to do anything. Take away our candy.
You could. But you could also just recognize from the form we just gave you in the last slide that this is that same form. I guess we should stop and appreciate that. Is this the same form as in the last slide?
Yeah.
It really is. It's just solved for R, which is a good way to see it too.
No, we converted
Oh.
color to parametric right now.
Ooh, good question, and it's easy. But I don't want to give this a
That's what that was.
In fact, there's nothing in the polar coordinates that you can't do in that you can't do in parametric. Just exclusively you could never ever use your function. So polar parametric.
Can you graph a line that is y equals x and y?
Oh, you mean like one that goes through the origin?
Yeah.
Thomas, he would have to be 0.
What?
He would have to be 0.
I'd have to be 0?
Yeah, he would have to be 0.
Yeah, but if you plug in 0, then you only get a point.
You would have to be zero.
What if you have an x? What if you have an n?
0 equals
That's the reason the reason I wrote it is so that it's not ever on the
I hear you can never. Oh, okay, I see what you mean now.
There's also another way. Grace, how's it going?
10 sign.
Don't cheat. Yeah, just recognize what is P and what is phi, people out there, and then draw a line, right? See if you can figure out from what P is and what phi is.
Well, yeah, but that.
No, did you get it?
You actually did.
Oh, wait, so a beta
Yeah, that's a
we didn't do that. Out.
Grace is doing it. Maybe she's not going to do it. All right, here. Give me that. All right. All right, we gotta do other things here. So, 3 pi over 4 is here. 1, 2, 3, 4. How's that? Does that look good? All right, homework. Homework is there are like a couple book problems, but then you have this sheet to look at mine. I hear you say you love Oh wait,
It goes like this.